Hi everyone, this is Mrs. Smith. Today I want to talk to you about analyzing units in an equation. I already talked to you a little bit about the different types of measurement systems and how we use the metric system. And so what I'm going to do today is I'm going to focus on the metric system and show you how when we're using equations, units play a really significant role. So first, in IB, you have the physics data booklet to reference anytime you take a test and for the papers at the end of the year. So this is a resource that you need to become familiar with throughout the year. I always tell my students, have that by your side for every class, for every assignment, because you need to become familiar with what equations are provided for you through the booklet and which equations you need to just know. And there are a lot here in the booklet, but again, there are still some that you might want to memorize. Whenever you're looking at these equations, and I have one little page here for you to reference as we're going through, and you can see over here there's a whole bunch of different equations on this first little sheet. The data booklet's very thick if you haven't looked through it. It consists of several sheets. And each one of these is a different equation. And in those equations, there are these variables, okay? The variables are just placeholders for different quantities. And each of those variables have units associated with them. So we need to be able to identify the units for each variable, and then we can see that the units on either side of the equation are equal to each other. When I was growing up and I was taking physics classes, I had to memorize a lot of the equations. So I would use this unit analysis method to make sure I memorized the equation correctly. Because if the units balanced out, that was a good indication that I may have done it right. Okay, so I have a little warning statement here. Make sure that similar quantities are measured in the same units. What do I mean? If you have a problem and they're talking about length and they keep saying meters, 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 that's good. They're all the same unit. But if the problem gives meters for one length and centimeters for another and millimeters for another, you need to make sure that you get all of those measurements converted to agree. So typically I would say go to the base unit, which would be meters. So anything that wasn't in meters to start, convert it to meters before you start plugging them into equations. It is desirable typically to have these units in the fundamental units, and I'll show you why in a moment here. If the initial velocity in a problem is given in meters per second, get out of my red highlighter here, in meters per second, but the final velocity was given in centimeters per second, what would you do? Well, like I just said, this is an example where you can see seconds are in both of them, so the time reference is the same unit of seconds. But if you take a look, we have meters in the numerator here and centimeters in the numerator over there. They don't agree. So we would want to convert this centimeters per second to meters per second before you even start into a problem. The next example, it says, if the velocity was given in centimeters per second and the acceleration in meters per second squared, what would you do? Well, again, I can see the time is in seconds for both of them. Seconds, and we have seconds here. Yes, they're squared for acceleration, but that's okay. And then the velocity is in centimeters for the length portion, where the acceleration is in meters. So this is an example where you would want to convert the centimeters per second to meters per second before you even start the problem. And then one last one. If one mass was given in grams and the other was given in kilograms, what would you do? Now, this is where I'm going to go back to this statement here, the second bullet point. It is desirable to use the fundamental units of a quantity. So I am going to choose to convert grams to kilograms because kilogram is our fundamental unit for mass. So I would convert grams to kilograms before I would start the problem. Okay. So I have some examples here. I want to show you how dimensional analysis, what I'm using right now, is going to show us that the units agree from one side of the equation to another. And like I said, sometimes this is helpful. Maybe there's a multiple choice question or something. It's helpful to be able to do what we're doing here in this lesson. All right. So we have three different variables in this problem. We have VAV, and that's our average velocity. And I know, and I don't expect you to know this. We're at the beginning of physics. I don't expect you to know the units for all these, so I'm telling them to you. The average velocity is measured typically in meters per second. In the numerator, there's this delta S, the triangle with the S. That means a change in position, and is also referred to as displacement. And that's going to be a length measurement. So it will be measured in meters. And then we have delta T in the denominator. That stands for change in time. And that would be measured in our time fundamental unit, which is seconds. So what I'm going to show you now, I'm going to plug in what the units are for all of these variables. So instead of average velocity, I'm going to show what the units are for average velocity. So I have meters per second equals, and then I'm taking the length, the delta S, the displacement unit, which is meters, and dividing it by, because that's what they do in the equation up here, right? That's division hidden under there, divided by the time unit, which is seconds. So look, this is showing us, yes, meters per second equals meters per second. That makes sense, okay? That's kind of confirming, yes, this is a good analysis that you're doing here. That's the equation. You can see that the units balance out on both sides, okay? And that's more of a straightforward example. Let's take a look at a couple other ones. All right, so we have a V, U, A, and T in this equation. So like I said, I'll let you know what these variables stand for. V stands for final velocity in this equation, and it is going to be measured in meters per second for the units. U is the symbol that IB uses for initial velocity, so that's also going to be measured in meters per second because they're both velocities. A stands for acceleration, so that is meters per second squared. And T stands for time, and that is just going to be seconds. All right, so we have all the units for the different variables, and now I'm going to plug them into the equation and see if we can watch how what's on the left is equivalent to what's on the right, because that's what equal means, right? Whatever's on the left-hand side is equal to the sum quantity, whatever that's on the right. So for V, I'm putting the units in for this unit analysis, meters per second. U, we said the units are also meters per second, plus A, acceleration, we said is meters per second squared, and then T is seconds, so we're multiplying that by seconds. Now, if it's easy for you, that's the same as saying seconds over 1 if you like having that as a fraction, like the thing that it's being multiplied by. So I need to make sure this all works out right. I'm going to look at what I'm bracketing over here and simplify it, because I have meters over seconds squared times seconds. Well, this second up here would cancel out one of those seconds down there. So then I would have meters per second equals a meter per second plus this one now simplifies to meters per second. So just like if you would add apples to apples, your answer would be apples. That's what we have here on the right-hand side. When I sum up something measured in meters per second plus something measured in meters per second, on the right side, it would be meters per second. And ta-da! We can see here that the units do equate on either side of the equation. Here's another unit analysis. All right, for this one, A with a little c stands for centripetal acceleration. So I know that accelerations are measured in meters per second squared. The V in the numerator is standing for velocity. That's measured in meters per second. And in the denominator there is an R, and that's like a radial distance measurement. So since it's a distance or a length, that's going to be measured in meters for the fundamental unit. So let's take a look at this one. On the left-hand side, the units for acceleration are meters per second squared equals velocity is meters per second, so I have meters per second, and that unit would be squared. And then in the denominator, I have meters. Now, I'm using this as a little fun algebra practice for you too. A lot of people, when they get to what's on the right-hand side there, kind of look like, what? How do I do this again? I know a lot of students at my school have this keep, switch, flip method that they've been taught. That's the way they think of it. So let's talk through this, okay? First of all, the meter in this meter per second in the numerator here, that's squared. So that means I need to square the meter and square the seconds, okay? And then I need to divide that fraction by a meter. Now, some people think it's easier to picture this as meter over 1 because in their head it's easier for them to process. I don't care, whatever works best for you. So for me, this means meters per second squared, that's the left-hand side, equals. Now, I'm going to go through, and if you take a look at the numerator here, I'm going to square that, and then I'm going to do keep, switch, flip. So I have the meters squared per second squared. So what I did was I just took care of that numerator. That's what I just wrote, squaring both things in that quantity. Now, instead of saying divided by, I'm doing that keep, switch, flip. So I kept the first, what was in the numerator. I'm switching divided by to multiply, and then I'm going to flip the fraction in the bottom. So it would be 1 over meters. Again, just refreshing your algebra here, folks. So if I look on the right-hand side, I have a meter down here that's going to cancel out one of the meters in the numerator. And I have meters per second squared equals meters per second squared, where yes, indeed, that shows that it is balanced on either side. Okay, hopefully you're getting the feel here for this method. It's just a unit analysis, and it kind of shows us, yes, what's on the left is indeed equal to what's on the right. I think this might be my last one. So we have a kinetic energy equation here, Ke equals 1/2 mv squared. So Ke, I think typically IB writes it a capital E with a K subscript. That is kinetic energy, and energy is measured in joules. And then the half is just the half. Mass is measured in kilograms. And velocity, we've already said on previous slide, is meters per second. So I'm going to start plugging in the units, and then I'm going to show you a little something. All right, so I have kinetic energy measured in joules. Fantastic. Equals 1/2 doesn't have any units, so I'm not going to include that. Mass has a unit. Mass is in kilograms. And then velocity has a unit. That's meters per second, but that is squared in the equation, so I'll have to square the units. All right, so this is interesting because this doesn't look like it's going to be equal. And this is where you need to have a little bit of prior knowledge. A joule is not a fundamental unit. It's a derived unit. So we can actually describe a joule with a combination of fundamental units. Okay? And the units that make up a joule are a kilogram times meters squared per second squared. Okay? So I have that a joule is equivalent to a kilogram. I forgot my G there. A kilogram times meter squared per second squared. So now for the joule, instead of writing a joule right here in the equation, I'm going to replace it by kilogram times meter squared per second squared, because those are the fundamental units that make up the derived unit of a joule. So on the left-hand side, a joule is equivalent to a kilogram times a meter squared per second squared. And that equals, on the right-hand side, mass was in kilograms, and now we have to square the velocity. So that means the meter in the numerator gets squared and the denominator of seconds gets squared. And if you look, ta-da, they are equivalent to each other. Okay? So the process that we just went through is something that you may realize you're doing in every equation, or maybe you don't. But it's important to realize that all of those variables have different units associated with them. And whenever we're doing mathematical operations with the number, we are also doing those same mathematical operations with the units. And the units should be equivalent on either side of the equation, just like the numerical values are. Okay, so this is something, again, you can use all of the time. It may be helpful for you. It is important to keep track of the units and make sure that they're agreeing whenever you're doing your calculations. All right, folks, I'll see you next time. Bye.